and go from there. So yeah, Michael, question number 1 and 2. I don't know if you guys saw, I added some more wording to those 2 questions out there due to one question that somebody asked. Probably won't let me in now. I say, okay, so all right, so this here is a circuit that we're going to build in lab. Okay, so these 2 questions number 1 and 2 here are basically your pre-lab work. So I tried to like put it in the homework so that you'll have your values when you do that. So when you come in to lab next week, we're going to actually be building this circuit in the classroom. And so the idea is that you want to have your numbers so you can just build the circuit, test it, I'll sign off on it, and you move on. Okay, so what this question is doing here is basically this 100 ohms resistor, this 100 ohm resistor down here represents the PLC. All right, and so remember that we are going to you know, for a PLC to read a value, and we haven't really quite talked about that yet. I think that's actually, I was planning on doing that maybe Thursday, but you know, a PLC, I may have said this before, but a PLC to read an analog signal, that current, if we're going to feed it a current, that current is going to be going through a resistor, and basically then the PLC is a voltmeter that's going to read the voltage across this 100 ohm resistor, right? And so the blue 100 ohm resistor down here is represents the resistance inside the PLC that we're going to feed the current into and get a voltage drop across that. So and I added some more wording here. I don't know, I just added it a few days ago, so I don't know if you guys saw it or not, but actually it was up here, the scenario piece. Basically what we're trying to do is build a sensor that outputs a 4 to 20 milliamp signal. So what that means is that in this circuit, okay, you have again, the blue resistor is the PLC, but basically we're going to have like a tank sensor where we're going to measure the level in a tank or something like that. And so potentiometer 2 is going to be like maybe connected to the float in a tank. And so when the water is low, then we're going to have a small current, which actually means that the potentiometer 2 is going to be maxed out at 2 kiloohms. But then as the water rises, the resistance in the potentiometer is going to go down. And so when the water gets all the way to the top, then the potentiometer would be at potentiometer 2, the second pot, will be at the minimum, which would be 0. Okay, so the second pot would be at 0, and therefore it will be at maximum current, right? So when the potentiometer is full, or excuse, well, when the tank is full, the potentiometer 2 is at 0, which means we're going to be feeding 20 milliamps into our 100 ohm resistor inside the PLC. Now, so the E is just a voltage supply to drive the current that we want to feed. And the problem is that we need to pick the voltage E and the resistance and potentiometer 1 so that we can generate a 4 milliamp signal when the potentiometer is at its highest, okay, because the current's going to be lowest when you have the most resistance, right? So when the potentiometer 2 is at its maximum value, then that is going to be 4 milliamps. And when the potentiometer is at its lowest, at 0, then we need 20 milliamps. All right, so basically we have two unknowns here. We have the voltage E is an unknown, and the value of resistance up here for potentiometer 1 is an unknown. Now these two values, once we find them, they never change. Okay, they're just the fixed values to give us a current somewhere between 4 and 20 milliamps. What's going to change is only potentiometer 2. All right, so to do this, I'm gonna put in the chat window here. If you don't have the chat window open, there's that like magenta kind of symbol down at the bottom for the chat, and you need to do that because I'm gonna put this in the chat window because I don't want to change my screen to something I can write in, because if I do, it might lock up on me again, like it did the first two times I tried to change my screen. So, all right, so what we're going to do is we're going to have case number 1. So in case number 1 here, we have pot 2 is going to be at its minimum, is going to be at 0. Its minimum is 0, which means that our we're going to have a current. So the current would be, let's see, the pot is, the current would be the maximum, which is going to be 20 milliamps, which is going to equal our voltage E divided by pot 1, whatever pot 1 is, plus the 100 ohms, right? And so that's just basically Ohm's law there. You have the voltage is, or the current, 20 milliamps is going to be E divided by whatever pot 1 resistance is going to be, plus the 100 ohms inside the PLC, because potentiometer 2 is at 0. Then you have case 2, where pot 2 is at its maximum, which is at 2000. Okay, 2000 ohms, which means that we're going to have the smallest current we can possibly get. And so Ohm's law again, but now Ohm's law is going to be pot 1 plus pot 2, which is 2000, plus pot, or that was pot 2, plus the 100 ohms. All right. And so for case 2, right, case 2, you got 4 milliamps is equal to this unknown voltage divided by whatever pot 1 is, plus 2100. Okay. And so we have two equations and two unknowns. And so all we have to do is just solve those. So you could solve, and you could solve for, say, like E. So E is equal to, using equation number 2, E is equal to 4, the 4 milliamps, times pot 1, whatever pot 1 is, plus the 2100. Okay. So now you can then solve for equation number 1 now. Equation number 1 becomes 20 milliamps equal to E, but now we know that E is equal to 4 times pot 1 plus the 2100, okay, divided by pot 1 plus 100. Okay. And so if you go through and solve that, you should get I believe the answer is E is equal to 10 volts. And look at the answers here just to double check. I'm going from memory because I can't really solve it in the chat window very easily. I'd have finished working it out, and I don't want to take that much time. So we'll go here and just double check the answer. Yeah, 10 volts, and the resistance is 400 ohms. Now, I know somebody sent me and they said, oh, I got 500 ohms. Well, you got to remember that there was 100 ohms there. So did you subtract that out when you got 500 ohms? Okay, so it sounds like maybe you did the math right. You got 500 ohms, but you forgot that 100 of those ohms are the PLC resistance over here. So pot 1 needs to be set to 4 ohms. Okay, so if you look at that, then if pot 1, which is equation 2, right, we want 4 milliamps. 4 milliamps is equal to 10 E divided by pot 1 plus the 100 ohms, right? Plus the 2000 ohms of pot 2. And so if pot 1 is 400 and E is 10, okay, then that should give you 4 milliamps. If I did my math right. Yes, 4 milliamps. And then if you look at equation 1, looking back at equation 1, we need 20 milliamps, which is equal to 10 volts divided by 400, which is pot 1, plus the 100 of the PLC, right? And so that gives you 20 milliamps. So those are your min and max, right? Your limits. Remember that analog signals are always between two limits. So those are your two limits. Your 4 milliamps is one limit, and your 20 milliamps is the other limit. And when do those limits occur? When pot 2 is either at 0, right, its smallest amount, which is going to give you actually the maximum limit, because you have the least amount of, you got the, let's see, pot 1, or excuse me, pot 1 doesn't change. If pot 2 is at 0, you're going to have the maximum amount of current, which is your max limit. And if pot 1 doesn't change, pot 2 is at maximum, you're going to have your minimum current. But see, your minimum current can never fall below 4 milliamps, right? 4 milliamps is your minimum current. You should never have a current below that. And you should never have a current above 20 milliamps. Okay. So like if you were to go in there and put, let's say that pot 1, let's say the tank was half full. So you were halfway in between your two values, then you should be at 12 milliamps. All right, I'm getting 6 milliamps out of that for some reason. But anyhow, as you adjust that potentiometer, it may not actually turn out to be a linear thing, but as you adjust that potentiometer, right, your maximum current you should ever get would be 20 milliamps when the potentiometer is all the way at 0. And your minimum should be 4 milliamps when the potentiometer is at its maximum. And so that was what we were trying to do with questions 1 and 2. And again, that's a pre-lab. That's basically a pre-lab assignment, so you need those numbers. When you read the pre-lab, I've got to, you have to, I ask you to solve it in the lab actually, but see, we already have that answer, so you can just record your answer at that point. But that was the questions number 1 and 2 in there. All right, so let's go ahead and I will go back to the slides then. And I just want to kind of go through here. So we're going to talk about the PLC networks. So there's a lot of different networks that are out there and available that are being used. Okay, so we'll talk about some of those. And then we're going to focus primarily on Ethernet IP, because Ethernet IP seems to be really becoming the standard. Okay, so we'll talk quite a bit about that. But when we talk about like encapsulation and the OSI model and that kind of stuff, keep in mind, even though we're focusing that on the Ethernet IP, is that that sort of stuff needs to be done for any sort of network communications that you're doing. You have to encapsulate the data, which means that you need to basically, it's like if you were going to mail a letter to someone through snail mail, for instance, right? You need to take the letter, which is the data, the information. You need to put it inside of that envelope, and then on that envelope you have to address it. So in the address you have to put city, the state, the zip code, and you also have to put like the street address and the number, the house number for that street address. And so that when you send that data, it knows where it's going. And then you have to also put the return address, so that when you send it, number one, that they know who it's from, but if something happens and it can't be delivered, then I guess the post office, right, they know who to send it back to, and they can send it back and say, there was no forwarding address, and this person's no longer there, or something like that. So we have the return address. So that information needs to be included when you send your information across the network. When you're communicating and you want to send that data, you have to, like I say, put it in the envelope, address the envelope so it gets off to the right place. And so you have to do that for anything but the simplest of communication, which is just serial communication, which is a one-to-one. But so we're going to talk about that. We'll talk about what this OSI model is, and then we'll talk about the TCP/IP model. And we're going to talk a lot about just the basic IP version 4 addressing and subnetting. All right. And we'll also talk about some devices and stuff. So that's what we're going to talk about. So the first thing I'm going to do is talk about protocols. Okay. And a protocol, in my personal definition of a protocol, it's basically a set of rules that need to be followed. All right. And so when you look at this picture, I found this picture out on the internet somewhere. I think this was in England or something. And if you look over here on the left corner, right, you can see traffic is just backed up like mad. And you can see that these guys here are just breaking all the rules and driving, they just want off the freeway, it looks like to me. And so they're going down a one-way road the wrong way, right? You see they're just weaving in and out of cars coming the other direction. So this is obviously like a one-lane road. I assume it's the on-ramp onto the highway, and all these cars are like, I'm getting out of here, and they're going the wrong way. And, you know, I mean, I don't see any accidents there at the moment, but, you know, that could cause an accident because they're going the wrong way down that street. Okay. And so, you know, we need to have protocols or these rules of how to how to drive. You know, we have, you know, you stop at a red light, you can go at a green light, you know, and you know, one-way streets or various things like that. We need to have those things in place, and that's true for any kind of communication that you are doing. All right, now this is actually in your book. Okay, so actually in the section 145 of your book, they actually have this picture in there showing the control logic system, and showing that like each one of these is kind of wired into a different module into this control logics PLC. And so one PLC can actually talk on all of these different networks simultaneously. So now there's a lot of different PLCs, or excuse me, protocols or networks that are available. Some of them are proprietary, some of them are open. And so I have a list here which kind of summarizes everything. So to communicate, you basically, you know, if you want to use something called DeviceNet, for instance, you need to have the proper PLC module. If you want to use Ethernet IP, you've got to have the proper communication module. If you want to use ControlNet, you got to have a module for that. So for each one of these networks, like I showed you over here, right, we're wired up to like all these. Here's ControlNet, Ethernet IP, DeviceNet, Data Highway, and we're wired into all these different sort of networks, and we have to have a separate module for each one of these. Now the different module types, there's something called Ethernet/IP. Now this IP, you've probably heard the term IP before, and for general use, IP stands for Internet Protocol, which refers to the addressing, as I was discussing before, and how we communicate what address, who we're sending the message to, and who did we receive it from, so we can send back a reply, that kind of stuff. But and when it's written like this, Ethernet/IP, IP here doesn't stand for Internet Protocol, it stands for Industrial Protocol. So this is a modified version of Ethernet that is dedicated, was specifically adjusted. I mean, it is Ethernet, which you have on your, you know, your computers and your phones and everything basically use Ethernet, or Wi-Fi version of Ethernet anyhow. And but this industrial protocol is specific for PLC and robot and automation communications. Okay, so it's a specialized version of that. Now there's some other ones that are here. There's you know, actually I'm going to start from the bottom of this. All right, so basically the original types of communications, there were two different things. One of them was called the ASCII, or just serial communications. Okay, it was serial communications. It normally used the ASCII code, which I discussed on Thursday. All right, but it's serial communication. Now the problem with serial communication is you're sending one bit at a time. And so if you remember with the ASCII code that we talked about, it takes 7 or 8 bits, and you're sending one bit at a time. So it's like just a very, very slow method of communication. All right, but it's open. It's very well understood, and it's you know, if you just need to send a little bit of data, it's very simple uh, and available to communicate with a lot of devices that maybe don't have Ethernet or DeviceNet or one of these other ones. Okay, so the ASCII communication is probably the original one, but it was very slow and very um, very limited in what you can do with it primarily because of the speed. Another option, which has actually been around for pretty much since PLCs started, or at least started growing in size, is something just called remote racks. So like when we look at this PLC up here, and we see all these slots in here for modules, and you see there's no empty slots. So this guy is full. But if you needed more inputs and outputs, what you could do is you could get a module that basically just said, hey, talk to another rack. So you can a whole nother rack like this, and you just put a module in it. So like right here where you see the blue and red wire coming out of this, that's the PLC. That's the processor itself, right? The rest of these are some sort of input-output card, whether it's a network communication device card or just simply wiring up digital sensors or analog sensors or whatever. So each one of these in here is a separate card, and you just have the one PLC. So, but if you needed more I/O, you could buy a second rack, put just a remote rack communication card in instead of the PLC, and then you could have access to all the other slots in the second rack. All right. Now, the problem with this is it's what we call proprietary. Proprietary means that if you had an Allen Bradley PLC and you're going to use a remote rack, you got to have a remote Allen Bradley card and a remote or a second Allen Bradley rack with Allen Bradley cards in it, right? Because it's all Allen Bradley. If you had Siemens, then you would have to, it would all have to be Siemens. Okay. And so, that's kind of, sometimes that's not very convenient because, maybe for a lot of different reasons, maybe you're looking for a certain type of I/O that Allen Bradley doesn't support, but Siemens does, or maybe some third party does. And so you can't utilize that using these proprietary communications. Okay. Another option is Data Highway Plus. Now, Data Highway Plus is proprietary. It's Allen Bradley's, and it was one of their first early attempts to communicate with multiple PLCs on some sort of network. And I mean, for the time, it was fine. It was good. It works, of course. The problem with it is, well, number one, it's proprietary, so it would only communicate with either Allen Bradley stuff or a company that purchased a license to build Data Highway Plus communications into their sensors or whatever. All right, but the big minus on Data Highway Plus is just the fact that it's really nowadays, this is 2021. Data Highway Plus has been around for a very long time. So when it first came out, it seemed like, hey, this is really fast and very cool, but nowadays it's considered very slow. There's another communication protocol, and this one actually came out of Germany. It was called SIRCOS, and this actually stands for Serial Real-Time. I forget what it stands for, but anyhow, it's an acronym. That's why it's all capitalized, and it's an open interface, and it's been around for quite a while, so it's not the fastest, but it does have a nice thing because it uses fiber optics. Okay, so the Surcos uses fiber optics, which means that, remember back in last Tuesday when we talked about all the different ways you get interference, and we talked about like your radio, like your cell phone. If you're standing by the machine with your cell phone, that is emitting radio frequencies that then get injected into your cable and cause noise inside of your signals. Well, Surcos is using fiber optic, so it's immune to radio frequency noises. So that's very, very, very cool. And I actually worked with Surcos many years ago. When I was working on my master's, I did a lot of work with Surcos systems, and it was really just coming into America, at least at that time. It was a relatively new technology, but it was very cool the way it worked. It's an open format, like I say, so anybody could download the specs for Surcos and build their own sensor or whatever to communicate on the Surcos network. All right. Now, Alan Bradley, after Data Highway Plus, they came up with something called DeviceNet, and DeviceNet is faster than the Data Highway Plus. Okay, and it's also, they opened it up, so it's more of an open format, which is kind of nice. But again, it's been around for quite a while, and so it's again considered kind of slow nowadays. ControlNet also, it's open. Not sure who actually created ControlNet, but it's an open protocol. But it's again, these are kind of considered on the slower side now. ControlNet and DeviceNet are much faster than these other ones. Okay, especially the bottom three. But they, well, I honestly, I don't know how much slower than they are than a remote rack. A remote rack actually may be pretty quick, but it'll only work in relatively short distances, and it's proprietary. So, but Ethernet is really seeming to become the choice now. Pretty much any sort of new devices that are being developed out there for communication on a industrial network are coming out supporting Ethernet IP. And the reason for that are a couple of different reasons. Number one is the fact that it's probably about the fastest communication of anything listed here. Another reason is that the technology is well understood, and the equipment like routers and hubs and switches and firewalls are extremely cheap compared to like ControlNet. So if you wanted to do ControlNet or DeviceNet, you got to buy special cables for these, and you got to have special cards for these, and it gets very, very expensive to utilize these. And again, the amount of data they can transfer is slower compared to what we can do with an Ethernet also. So Ethernet really seems to be becoming the standard. All right. So so I've talked about proprietary and open networks here. All right. So the PLC can act as a data hub or a data concentrator. So one of the things that means is the fact that we talked about attenuation of signals last Tuesday, right? We were talking about the attenuation of signals. And what that means, right, is as you're trying to send those bits, those ones and zeros, from one device to another, okay, you are going to get attenuation. And so what a hub or data concentrator does is it's kind of a middleman, and all it basically does is take that signal and resend it fresh, so that you basically, as you transmit that data, when it gets to the other end, it's starting to be attenuated and the voltage is dropping on you. So what this is going to do is the hub just receives that signal and then resends it out the other port, but boosting the voltage back up. Okay, so when we talk about Ethernet or Ethernet IP, a standard Cat5, we'll talk a little bit here later about exactly what the Cat5 or Cat6 cable is, but a standard Ethernet cable is only good for 100 meters, which is, a little over 300 feet. So Ethernet is only rated at 100 meters. After that, they consider the signal has been attenuated too much, and so you're not getting proper signal to the receiving end. And so, by putting a hub at, say, that 100 meter, or maybe a little bit before that, even before it gets down that, but then you can double that to 200 meters. So you can have a length of run of 100 meters, put a hub there, and then you could run it another 100 meters. Okay, where without the hub, you can't run it that far. All right, so a lot of these slides I pretty much talked about in here. Again, I'm just highlighting the industrial protocol piece here. Now, one thing though, when we talk about any network communications for industrial use, is the fact that we need to think about security. All right, so when you are communicating data that is controlling your equipment, if somebody was able to hack into your network and send false instructions, it could cause damage, it could cause injury, it can just do a lot of bad stuff. So my recommendation is that, and I hope any company that's doing this, you're very, very careful, and your industrial network must be a separate network. Okay, so you need to keep that separate network, and if you're going to connect it to the internet, you need to do that in a very secure way. So you need to be very careful with that. Yes, Brian, good point about there was something called the Stuxnet virus. This was years ago, but some people claim that it was the Americans that created this. Some people claim it was the Israelis. But there was this virus that attacked nuclear, these plants that were trying to basically refine uranium over in Iran, I believe it was. And so that's why some people suspect it was, one of the governments, like the American government or the Israeli government. I don't know if that's true or not, who created this, but this virus was created that infected this equipment. And so think about this. Let's say that you're running a motor or something, and you have a maximum amount of load that you can put on that. You have a maximum amount of current you can run through it. And so typically what we're going to do, one of the things we would do, for instance, is put like a temperature sensor on there. And so we'll put a temperature sensor in there and say, if it gets above, 100 degrees Celsius, or, whatever temperature that we say it's getting too hot, we need to either, turn the fan on to cool it off, or, shut it down, or at least slow it down so it's not running so hard that it's going to melt down because it's too hot. So if you were able to get into that network and interject into that information, if you were able to send in data that says, hey, the temperature, max temperature is 100 degrees. and let's say that, the sensor was saying, hey, we're at like 99.9 degrees. But if you were able to go in there and modify that so that now it only says, oh, well, we're only at 50 degrees Celsius. We're nowhere near, too hot. We're lukewarm. Let's crank it up, and so you could like trick this equipment into running much hotter, much faster without turning on the fans and the other cooling equipment or anything like that, until the stuff just basically, got too hot and was, ruined at that point and didn't work anymore. Okay. So that's why, you need to make sure that you have proper security. Okay, and to me, one of the downsides, or the big downside of using Ethernet IP, and really the only, one of the only two downsides to me is for using Ethernet IP, is the fact that the security, I mean, you need to do it proper. If you do it proper, security will be okay, but you need to make sure you do it properly. One huge issue I see with Ethernet industrial protocol networks is the fact that most of these are little devices that don't have a lot of processing power. So like when you're using your computer right now, when you're using Blackboard here and you're connecting into this video, right, you're using a 64-bit computer that is encrypting all this data and sending it across the network in a very secure way, right? But that's a 64-bit computer that you're running. Even your phone, if you're even doing it on your phone, right? These are your phones have like four cores on those processors, so that they can encrypt all this information and send it across securely. And one of the problems that I kind of see with these devices that we are hooking up to these networks do not have that kind of processing power. They cannot do, 128-bit encryption or whatever type of communications, a lot of them. And so, you need to make sure that, nobody can get into your factory network. Okay. Another issue that I kind of have with Ethernet IP is the fact that it doesn't truly provide real-time guarantee for packet delivery. If we go back and look at like the Circos protocol, for instance, what I mean by real-time is like when let's say you're filling up a tank full of acid. Okay, so you're pumping acid into a tank. And, so you've got your sensors in the tank telling you how full the water is. And let's say that your sensor, let's say you're doing this on the network, and you may have experienced this like at home when you're watching TV or whatever, that, you're streaming TV off Netflix or whatever. And, it seems like Saturday nights, especially, right? Everybody's sitting there streaming, especially nowadays, since with COVID, people don't go out as much as they used to. And so everybody's sitting at home streaming movies. And all of a sudden you notice that it just kind of, starts spiraling, this little spiraling circle or whatever, because it's buffering, because the network has slowed down. It's not getting its data. And so what Ethernet IP does when it sends its data, it guarantees, the way they do it, they broadcast the data out. So they guarantee that it's being transmitted every 20 milliseconds or whatever the time is set up for it. But when they send that data out, they don't have a guarantee that it was actually received. And so therefore, you don't know 100% whether the guy got the message or not. So, if you're the guy up at the top of the tank, the sensor, really, and you're supposed to send down your message and tell the pump to stop because it's full, And, you know, this guy over here starts streaming his latest Netflix. The one I've been watching was Lost in Space, the new Lost in Space. But, you know, so I start streaming my Lost in Space, and it slows down the network, and the message doesn't get through for 3 minutes. Then all of a sudden, right, you got acid spilling over the top of your tank, right? And so that would be very, very bad, right? So it's very important when you're talking about, you know, working with controls, right? The whole purpose of having automated controls is the fact that they say, hey, you know, the tank is full, shut off. And so if you don't get that message, you don't shut off, now you've got problems. And so it's very important that you don't have interruptions. So when we go back and we look at these protocols like Circos and DeviceNet and ControlNet, those things had a very fixed guarantee that the communication was going to happen every, you know, it may only be every 100 milliseconds, which, you know, is really seems kind of slow. But the fact is that, you know, within, you know, 1/10 of a second, you're going to get an update. So that if that sensor says, hey, I'm full, that's going to be delivered to your PLC within 1/10 of a second. You're not going to get this where it's like spinning around, waiting and waiting and waiting, and you may wait 30 seconds, and now you know, it's too late. You've got acid, you know, spilling out of your tank or something along those lines. So you need to have real time. And I've been reading a book on Ethernet IP, and from what I can gather from it, they try to do real time. To me, I'm still not convinced from what this guy is saying in this book that it is true guarantee that it's going to be delivered. Okay. They guarantee that it's going to be sent. The message is going to be sent at that time, which is good, but they don't have a guaranteed delivery because there's the way they're sending it. Maybe I'm misreading the book, but anyhow, so that's my pet peeve on Ethernet IP. All right, so we talked about ControlNet, okay, and one of the things I did kind of highlight here is this whole thing about time critical or real-time communications. So, you know, when these things were designed, okay, when ControlNet was designed, ControlNet, obviously by the name, it was designed for controls. And so it was designed, one of the major design factors was getting the data transmitted and guarantee receivable in a guaranteed real amount of time. So I know that I'm going to get that data message, okay? And the again, just one more time back to Ethernet. The problem with Ethernet was originally designed without thinking about this aspect of real time. And so when they added in the industrial protocol, they've done a lot of things to try to guarantee it delivery, but it's just the base of Ethernet never had that to start with. Where ControlNet and DeviceNet and everything, they always had those built in. Okay. All right, there's the acronym for Circos, serial real time. See, Circos has the word real time built right into the name. All right, and so again, it was designed for this concept of real time. I guarantee that, you know, within whatever amount of time that the system set up to communicate, whether it's 20 milliseconds or 100 milliseconds or even really slow, 1 second, but I guarantee, you know, in that time frame, all the messages are going to be delivered. Okay. All right, so I'm just gonna, I've talked enough about those in there. Well, let me point out, I do have a question or two where I ask about whether these things are proprietary or open. So I'm going to tell you right now, remember that Data Highway Plus was proprietary and that remote racks are proprietary. And if it's not one of these two, it's an open protocol. So that'll help you with that one question that will pop up from time in quizzes or homeworks or even exams. All right, so let's talk about cabling. All right. We already talked on last Tuesday, the fact that a cable is a group of conductors all inside of one, connected together and inside of one outside insulation. Now, when we look at Cat 5 and Cat 6, okay, these are pretty much the standard. There's also a Cat 7 out now, but for most of your PLC communications, 5E would be at least the minimum required standard. Now, we talked about something called Crosstalk on last Tuesday as one way of communication issues. And so Cat 5E it's got 4 pairs of wires that each pair are twisted to minimize crosstalk. All right. Cat 6 here also has 4 pairs, which means there's 8 conductors in there. Okay, and they're set up as 2 pair, or as 4 pairs. There's blue, white, brown, white, orange, white, and green, white. So those are the pairs in there. They're color coded. But Cat 6 has more twists than Cat 5E does. So it has a tighter twist to help minimize crosstalk even more. So Cat 6 is rated for a higher speed of communications. It's still only rated for 100 meters, but it can handle faster communication speeds than Cat 5E. And the other thing that Cat 6 does is it puts this insulator. You see this part sticking out here? That is like a separator. That's a piece of plastic that is a separator to keep the 4 pairs separated from each other. Where in Cat 5E, they're just kind of all twisted around each other then. So they put this separator in there to help crosstalk between the different pairs. All right. But for the most part, Cat 5E should work for most of what you're doing with PLCs. Okay. Cat 5E is a little easier to work with because it's not twisted quite as much and it doesn't have that middle piece there. So it's easier to work with those. So here's just a little chart showing the difference. Okay. Cat 5E is rated for 1 gigabit per second or 1,000 megabits, right? That's 1 gigabit. But Cat 6 is actually rated for 10 gigabits, at least up to about 55 meters. So it can't go the whole 100 meters at that speed. But at about 50 meters, it's good for 10 gigabits. So about 10 times as fast over at least a shorter distance. Now, the connectors that we connect on there is the RJ45. That's the standard connection jack. Okay. And it has this little plastic clip down here. I don't know if you can see my mouse moving down there, but it has this little plastic clip. And so when you push this in, that little plastic clicks in there and will hold that clip in. So to take it out, don't just yank on these things and yank them out, you'll break the clip. So you need to depress the clip and then you can it'll just slide out. But it'll slide in and it'll click and then that'll hold it in there and it stays in there nice and firm. Okay. Unfortunately, we do have some in the classroom where people have yanked them out and broke those clips off. So it'll still work as long as you just make sure it stays in there and doesn't get any kind of pull on it, because just a little bit of pull might break your connection. All right, now there's 2 types of wiring, I already told you there's 4 pairs, right? Green, green, white, orange, orange, white, blue, blue, white, and brown, brown, white. Those are the 4 pairs. Now, how do those go into this RJ45 connector? Well, there's something called the 568A wiring, which starts with green, white, green. And then there's 568B, which is orange, white, orange, okay, and then goes on. So they're the green and the orange get actually they all get flipped there, right? So you can see all the colors are kind of switched around there. Now, if you have something called a straight through cable, a straight through cable is a B to a B, or it could be an A to an A. I almost never see an A to an A cable when you buy them. They almost always come as B. They always start at orange white. You can tell because you just look at the jack and you can see in there the color, and you can see whether the colors on the left are orange or if they're green. Okay, so you can look at the cable, look at the connector, and you can see in that connector whether it starts with orange, white, orange, or green, white, green. So that'll tell you whether it's an A or a B. Now, if you have a B on both ends, that's called a straight through cable. If you have an A on one end and a B on the other, what you're doing is you're crossing. See, your 1 and 2 here is going to 3 and 6 on the other side if you're going from A to B. And what that means, see, when you have your PC is trying to say talk to the PLC, you're sending data. So if you're sending data, then the PLC needs to receive the data. When the PLC is sending data, it's transmitting and you need to receive. And so those are different connections. Okay, so 1 and 2 are transmit lines, and like 3 and 6 are receive. Okay, or are kind of like the receive side. And so if you're going to connect your PC directly into the PLC, you have to use the crossover cable. Because if you use a straight through, then you've got transmit to the transmit and receive to the receive, and it's not going to work. So the crossover runs these wires. They're green over here, but then the green goes into different connections on the other side, which are receive connections. Where if you're using a switch, okay, a switch or a hub, or like a Wi-Fi router that's got, RJ45 ports in it, okay, that's a switch. Okay, if you're using those, then you use a straight through cable, because the switch or the hub, actually they have the receive and transmit flipped so that you can just use straight through cables. So most of the time you're going to be connecting through a switch or hub sort of device, and you want to use a straight through. But if you're going to like take your laptop and walk directly over to the PLC and plug your laptop directly into the PLC, you need to use a crossover cable. Okay, so it's important to understand the difference between those. All right, so the question is that if the cable broke and you just try to connect it together with wire nuts or butt end connectors, and just try to patch the middle of the cable, it will not work very well. Okay, it may work as long as the distance is kind of short. Okay, but in general, I would recommend that you replace the cable, or if it's just broke at the one end, you can it's pretty easy to put on a RJ45 connection. Okay, takes practice to get good at it, but they make special crimpers for RJ45 jacks, and you just strip the wire and you can put that on there. Yeah, if your cables got cut in half or somehow and you just try to wire it up, part of the problem is that when you're running those wires together, you're missing that winding, right? So remember I talked about the twisting in here. If we come back to this, you see how these are twisted together and you get that crosstalk. The twisting minimizes crosstalk. But if the wires, if you like try to patch it up with wire connections, then to wire up those wire nuts, you're going to have to untwist this so you can put the wire nut from blue to blue and blue white to blue white, and you're missing out on that twisting, which is going to give you more interference at that point. And that's what's going to cause it not to work very well, because you're trying to send, the one thing, as I mentioned before with Ethernet, the nice thing about Ethernet, you can send data fast, right? Ethernet is very fast communication. But the problem with that fast communication is, it's very subject to noise. And so that's why using something like wire nuts or butt end connectors, you're going to lose that twisting in there when you try to wire them up, because so it may work, but especially on shorter cables, the longer the cable, probably the worse it's going to be, because there's going to be more interference and the communication is going to be unreliable because you're going to have more noise injected into it. All right. So one of the things that happens when you send stuff across an Ethernet, I talked a little bit about it with ASCII last week, right? When you send data across the network, you need to kind of know, did it get there? Well, what they do with these high-speed communications is they do something like I talked about the parity bit for ASCII last week. Well, they do basically the same thing, but they do it with what they call a CRC, Cyclic Redundancy Check. So part of the sending of the data, you send the data, but then you also send a value that basically what you do is you add up all the ones. Just very simply, you kind of add up all the ones and count how many there are, and you count how many zeros there are, and you kind of compare that. So when you send all this data, you also send this error checking value. And so then when it gets received, it checks the data and it checks the error data, the value. It's called a cyclic redundancy check. It checks it against that check value, and if they don't match, they automatically, this happens without us doing anything. It's built into the Ethernet, just the definition of the Ethernet. It resends the data, and it's like the receiver says, "Hey, I got some data, but it doesn't match. There was some kind of error. Resend it." All right, and this is one of the things that'll sometimes slow down your communications, is because something like that, where you repaired that wire, you got a bunch of noise, and it might kind of be working, but it seems to be really slow or something. And the reason is there's lots of errors, and so they're asking the sender to resend it multiple times before they get it correctly without junk in there, that the data came across correctly. Okay, but excellent question there. Yeah, so yeah, you could try and do it, but you lose reliability there, because you're, like I say, you're basically losing that twist when you make those connections, right, you've got to untwist them some so that you can get connected. And that is a big open area, which is going to allow noise into the cable, into the conductors within there, and so your data becomes less reliable. You probably have to ask to have it resent multiple times. You'd be like, I can't quite hear what. All right, so looking at network protocols, okay, one of the things I just talked about was like, hey, if the data came wrong, resend it. Okay, so you have to know, number one, how fast are you sending it? How much are you sending? Okay, what happens if two people on the network try to send it at the same time? What do you do? All right, it's kind of like what if you're coming up to a four-way stop, and there's three cars coming up at the other three directions. Who gets to go first, right? There's rules for that. And same thing here, you got four different computers or PLCs or whoever on the network trying to send all at the same time. What do you do? How is that handled? These are things that have to be built into your communication protocol. Okay. All right. I found this video. This video was actually from 2012. Okay. And I just thought it was very, very interesting in here to watch this. And they focus on the human factor in this video, which is very nice. But they also show FedEx's data center. If I remember right, it was in Tennessee. And they said, like, this is like the busiest airport in the world after midnight, because FedEx, all the planes fly into this airport. And then they offload all the planes, all the packages off the planes, and they run them through this huge sorting thing. Now, I'm not going to kind of run this entire video for you here, because videos through a video don't seem to work. But I do want to try to at least get to this one spot.
Maybe a couple weeks away, but for
I recommend that you watch this video. It's very cool. But I want to see if I can find this one spot in here. Okay. So here are all these packages, and you see there's people sorting them. Okay. But then there's also, once they get into it, they start flying along on these conveyor belts, right? And so they have these barcodes on them, of course. And you see these things just flying along and being directed here and there. Okay. And right there, that was the spot I was looking for. Did I miss it again? Okay, so watch this bar come out right there. Okay, so these packages are just flying along down this conveyor, and all of a sudden, boom, here comes this one out there, because they scanned it, somewhere before this. They scanned that package, they know where it's at, and now they've got this bar pushing it out here. And so this box is going to go down this chute and get loaded on the plane to Hawaii, or wherever that this chute is being directed at. So all the packages going down this chute are going going to that plane and going to end up in that state or that location. All right, so I think it's just very interesting to kind of watch that. And as you watch this, think about all the sensors in there. Most of them are barcode sort of things and stuff, but they, you got to know exactly when that bar's got to come out at exactly the right time to push the box down the chute. If it's a little fast or a little bit slow, it's just going to jam it in to the sides, right, and make a mess of things. So it's just kind of, I think it's just very interesting to kind of watch that and see how, and you know, all these warehouses and things now are like this, where everything is just so automated. And so these sensors and these controllers are so critical. Okay, so it's not just for manufacturing, it's even just for warehousing and shipping and things like that. All right, so I already kind of talked about encoding. Okay, what we have to do is we have to take our data and put it in a form that we can transmit. And we also have to do error checking, because we need to know that, you know, after we've sent it, whoever received it, they need to know that they received it correctly. All right? And so we can do that through pulses of light, which would be like fiber optic, or electrical pulses, electrodes, or of course, you know, Wi-Fi or some sort of radio wireless communication. Okay. Encapsulation refers to actually taking the data and, you know, as I mentioned before, it's like putting a letter in an envelope, and then on the outside of the envelope, you have to put the address information, where it's going, and also, you know, throw in the checksums. Okay. All right, so this is just kind of a slide trying to show block format here. So you have your data, and then you add on some information, which may be like, say, your house address, and then you add on the street address, and then you add on the city, state, and zip code. Okay, so you got to add on these different pieces of information. Okay, and so you basically are building these packets. They usually use the term for Ethernet. They call them packets. Okay. All right, so when we look specifically at Ethernet, okay, there's what they call the Ethernet frame, which is that outer frame. And then inside of that, you have the IP packet, which is now this, in this case, it's IP by itself. It means Internet Protocol. And that is like the street and the house address. And then they have something called like the TCP segment. Okay, so the TCP segment is kind of like another address. So let's say, like, you know, at my house, if I get a package at my house, I'm lucky, right? Most of the packages come and they're in my wife's name or my kid's name or something like that. So that TCP segment would be maybe like, you know, who is actually going to, who it's going to. All right. And in Ethernet terms, that's usually basically referred to as a port. So you have like, if you're sending it to a web server, it would be to port 80. If you're sending it to a mail server, it's like port 25. Okay, so they have like different port addresses in there. Okay. All right, so when we send the data, there's actually different ways we can send the data. We can do what I think people normally think about as communications, which is a one-to-one. So a one-to-one is kind of a telephone call where you pick up the phone and you dial a number and you talk to the person on the other end. Okay, one-to-one, that's called unicast. Then there's a multicast. Multicast is basically what we're doing right now. Right, you guys everybody's here is logged into this Blackboard, and now I'm talking and all of you are listening, except for the three of you who already fell asleep or whatever, but or maybe you're all asleep, I don't know. But the multicast is like one to many, like me speaking to you as a class. And then the broadcast would be one to all. I think of the broadcast basically as like a radio. you think about there's a radio station out there, and see, thanks, Anthony. Okay, you must have at least woke up for that much to send that, so I appreciate that. But the broadcast is like the radio station where they're out there transmitting, whatever music or whatever they're sending out, and they have no idea who's listening to them. Like right now, I know that at least one person here did hear me, which makes me feel better. I'm not talking to the void, but it's kind of, with the radio, you got those announcers talking and playing music. Okay, I got at least two people there. Okay, and we they don't really know whether it got there or not. And that's what the way Ethernet/IP industrial protocol is broadcasting its basic data. Okay, so with Ethernet IP, they actually use both of these. They use the unicast and they use the broadcast, where they just kind of broadcast it out there, but they don't know whether it got received. And they also do support one-to-one, and they probably support one-to-many. I haven't got to that chapter yet, I guess, but I don't know if they do. Okay. So, but anyhow, when we talk about addresses are very important. Okay. And so when we talk about like a switch, before I was talking about your switch or your that you hook your PC and your PLC into. In the classroom, we have these blue switches on the on top of the desk. You probably know this from PLC 1. And so you need to plug your PLC into those blue switches. Okay. Now the switches communicate this, and the PLCs on the Ethernet, they communicate through what's called MAC address. So that's like a hardware address, and every device on an Ethernet has to have this hardware address or MAC address. Okay, and it will show up like when you look at your settings. Actually, when you look at, okay, I actually have a PLC right in front of me right now. This one's called a Click PLC. But if you look at this, and you're probably not going to be able to see it on here because I got to put on my glasses here or something somewhere. Okay, well, I do not see it on here. Unlock. Okay. Usually they post on here what the MAC address is. Okay. And I am not seeing it on here, but they usually post what that MAC address is. Okay. I know for a fact the Allen Bradleys do. I'm not sure where my Allen Bradley, I got an Allen Bradley around here somewhere, but they post on there what that MAC address is. Okay, and then we can view that, and we can actually communicate to those using some special software. The IP address is an address that we assign. Okay, so we can assign them to whatever addresses. We get to choose the IP address. The port number is basically designed by what sort of communications you want to do. I already mentioned this. This was the TCP piece. If you're doing web, if you're communicating on the internet, on the web, going to Amazon.com or Blackboard.edu or whatever it might be, or if you're doing email, it would be port 25 and those kind of things. Okay. All right. So the MAC address is a 48-bit value. Okay, and it is on what they call layer 2 of the OSI, which are just these different layers. So we have the MAC address, is layer 2. Layer 1 is actually basically those pulses of light or electrical signals I mentioned before. And then you have your IP address. So the IP address is the third layer of this model. And the IP address here, this is the version 4, which is a 32-bit address. And it's broken up into 4 octets. Oct meaning 8. So there's 8 bits. This is 8 bits. This is 8 bits. This is 8 bits. And this is 8 bits. So put them all together and you get 32 bits. Okay. All right. Anyhow, so here is the ISO model. And this is just kind of a model that they put out there. I'm not too concerned about that. Just know that the OSI model has basically 7 layers. And then the TCP model. The TCP model simplifies these, like these 3 data layers here in green are the application layer in TCP. And then the transport model, which is our TCP, is basically the segment, the light green. All right. And so there's 4 layers in the TCP model. They group some things together. Okay. And that's about all I care about the models for this class. Okay. We did the binary conversion last class, so I'm going to skip over that. But I want to look at the IP address. Okay. So when you look at an IP address, you have 32 bits. I'm trying to find a slide here. So you have 32 bits in an IP address. However, that IP address contains 2 pieces. It contains what we call the network address and the host. Okay, but how we break that up is kind of our choice. Well, at least it's the network administrator's choice. Okay, and so like when I say network administrator, like right now, you know, I have Roadrunner, or what do they call themselves now? I think they changed their name, but you know, they basically, when I connect my Wi-Fi router into them, right, for internet access, they give me an IP address, and when they give me that IP address, they define how many of these 32 bits are the network and how many of them are the host. And so this is kind of an interesting thing here, because it's very, very important that the devices on the network understand the difference. Okay, and so you see here a Class A network only has 8 bits for the network, which means that you can have all these other bits for hosts. But a Class C network, like if you look at Class C only has 8 bits for the host. Okay, so I'll put this in the chat window here. So 8 bits for the host in Class C. Okay, so you got 8 bits for the host. Now, the problem with this is that when you look at this, let's say that you had an IP like 192.168.0.1. Okay, now that means that the 192.168.0 is the host, or excuse me, is the network. It is the network piece. And so what they do is they write 192.168.0.0. And so this right here IP address is already used. You're not allowed to use it because it defines the network. Okay, so 192.168.0.0 is the network. And if you do a 192 168.0.255. This is the broadcast. So remember I talked about the broadcast before? So this is a broadcast address. So this means that you're sending it to everybody out on the network. Whether they're listening or not, you're broadcasting it out there. So you can never use the .0 or the .255, which means you're allowed to use the values of 192.168.0.1 through 192.168.0.254. So this means that you can only put 254 devices on your network. Okay. Now, typically, when you go out and you buy a Wi-Fi router, for instance, for your home, it's going to use a Class C address like this, which means that the total number of devices that you can put on your network is 254, because you're not allowed to use the .0 number. It's reserved for the network, and you're not allowed to use the 255 because it's the broadcast. Now, when do you use the broadcast? Well, we use it all the time. When your computer first boots up and connects, it normally uses what we call dynamic addressing. So what that means is when your computer first boots up and tries to talk on the network, it doesn't have an IP address. So what it does is it broadcasts, it sends it out to the 255 number, which means I'm sending it out to everybody out there. I'm like, somebody listen to me. And then your Wi-Fi router, right, it's going to say, hey, this is your IP address. So the device you're connecting to, it's one of its jobs is to say, okay, here's your IP address. Okay. But the problem is when your computer boots up, it doesn't know what IP your router has. And so it broadcasts it to everybody, and everybody else ignores it. But if it's a device such as a router that can hand out, also, technically routers don't hand out IP addresses. That's a DHCP server. So it's technically a separate device, or at least software package that actually assigns that dynamic IP address. But again, your PC, when your PC boots up, it doesn't know who it's talking to, and it doesn't know what IP to use. So it broadcasts out there and says, hey, somebody talk to me. And then it'll assign an IP address to that. So if you're using dynamic, which they call DHCP, what they call it, DHCP, okay, dynamic host control protocol, and that's when you use that broadcast piece, okay? Or at least one of the times you might use a broadcast, maybe not the only time. All right, so now the problem with this, though, is the fact that if you have an IP of 192.168.1.1, the question is, can you talk to somebody who has a 192.168.0.1? Can you talk to that other machine if you have a .1.1 and they have a .0.1? And the answer is no, not if you're a Class C network. That means these are two completely different networks. And if they're different networks, they won't talk to each other. So what you have to do is go through a router and go through a gateway and be passed on to the other network. Okay, so for you, if you have a .1.1 in your Class C and the other guy has a 0.1 in these Class C, you can't talk to them without a router. Okay, so if you like had on your laptop, I mentioned earlier, you take your laptop, plug it directly into the PLC. If the PLC is talking on the 1.1 with a class C, your laptop's using 0.1, PLC's 1.1, your laptop's 1.1, and you plug them directly into each other, and you're using the crossover cable like you should be, they will not talk. Okay? They will not talk because they think they're on different networks, even though you physically wired them together. All right. And so that takes us to something called the subnet mask. The subnet mask is what you use to define how many bits are being used for the network and how many bits are being used for the host. Okay. So your subnet mask is a critical piece to the network. So you need to see if you changed your subnet mask. So a class C subnet mask is 255.255.255.0. That's a class C subnet mask. Now, if you change that to 254.0, now if we went back and we talked about the 1.1 and the 192.0.1, these two could talk to each other now because they would be on the same network if they were using the 254 network. Okay? They would actually be on the same network and they would be able to talk to each other, even though, like if you had them plugged in directly to each other. Okay? So now this is not a class B network. The 254.0 is not a class B. It's called modified class C network. But that's why it's so important that you understand the concept of this subnet mask and how it works, because you, like I say, you could literally plug your laptop directly into the PLC with a good crossover cable, not one connected with wire nuts or whatever like that, but it's a valid working cable. You plug them in and they won't talk because they think they're on different networks, even though they're physically wired together. Okay. And so the subnet mask and understanding the difference between the network and the host is very important. Okay. All right. So, I'm going to just we're about out of time here. So I did talk about the Stuxnet. I did have that listed down here, and I have a link. So if you want to read more about this Stuxnet virus on there. But I just want to highlight here, and then we'll finish because we're out of time. So protocols, I could say my definition of protocols is basically it's a set of rules for doing communication. Okay. Encoding is how we're sending the data, whether we're sending the data through pulses of light, fiber optic cables, or electrical pulses inside of a copper wire, or through radio communications through a Wi-Fi. Encapsulation is where we kind of take the data. It's kind of the envelope. We take the data, stick it in an envelope, and then we put the address information on the outside of the envelope, and we also do our error checking, so we throw in the error checking information in there. Okay. We talked about the subnet mask and how the IP address has both a network portion, which is kind of like the street address, and then the house number part, which is the host. Okay. And then talked a little bit about the devices. For Ethernet, we have a hub, which is basically just a amplifier. It receives the signal and then retransmits the signal to, which does actually two things. So one of the things, it'll amplify your signal to give you further distances, but the other thing is it allows you to connect multiple devices into the same network. Okay, so a hub will do that. Now, it used to be that you would buy a hub. Nowadays, you seldom ever buy a hub. What you buy is what we call a switch. And the difference is that switches are a little bit smarter. The problem with a hub is they didn't know who who they were going to send the data on to, so they send it out to everybody connected into the hub. Where a switch, on the other hand, it looks at that hardware address I talked about, and that hardware address is encapsulated into that packet, and it'll send it out to just the person who it's supposed to go to, whether it's your router or whoever. So, and then when the data comes back, it sends it just back to you, not to everybody connected into the switch. So hubs used to be used a lot because switches were expensive, but the prices of switches have dropped so much that nobody would go out and buy a hub because the switch is more efficient and cheap, just as cheap anymore. So, and then we talked about security. All right, so that pretty much covers it. A lot of material there.